Hello everyone, welcome to Math and Chemistry channel. My dear students, today my topic is linear combination of atomic orbitals in quantum chemistry. So this method is also known as LCAO method. So what is linear combination of atomic orbital or what is LCAO method? So LCAO method is approximation that how to construct molecular orbitals. We know according to linear combination of atomic orbitals, molecular orbitals are formed by combination of atomic orbitals. When atomic orbitals combine, they form, like if we have two atomic orbitals, suppose we have two atomic orbitals, and when these two atomic orbitals overlaps or when these two atomic orbitals combine, they form two molecular orbitals. One molecular orbital is of lower energy, which is known as bonding molecular orbital, and second one is of higher energy, which is known as anti-bonding molecular orbitals. Okay, and the electrons now will be present in the molecular orbitals. Okay, initially electrons were present in atomic orbital, but after the formation of molecular orbitals, now electron will be present in the molecular orbitals. Okay, now these molecular orbital, which is bonding and anti-bonding, these are associated with some wave functions. So the wave function for molecular orbital, it is denoted by psi plus, and the wave function for anti-bonding molecular orbital, it is denoted by psi negative. As we know, bonding molecular orbital is formed by constructive overlapping of atomic orbitals. Similarly, this anti-bonding molecular orbital, it is formed by the destructive overlapping of atomic orbitals. Okay, and these bonding and anti-bonding molecular orbitals, these are associated with some energy, right? And the energy, let's suppose the energy of bonding molecular orbital, it is E plus, and the energy of anti-bonding molecular orbital is denoted by E minus. This positive and minus just represent constructive overlapping, minus represent the destructive overlapping. Okay, when electron is present in bonding molecular orbital, it favors the bond formation, and when electron is present in the anti-bonding, or when electron enters in the anti-bonding molecular orbital, it does not favor the formation of a bond. Okay, so let's see we will understand linear combination of atomic orbital for hydrogen ion system. Okay, so hydrogen ion system is represented by H2 plus. Okay, so here we have two nuclei. Let's suppose the first nuclei of hydrogen atom is represented by HA, and HB represent the second nuclei. And here we have only one electron. Okay, this system is having only one electron. Okay, now this electron is considered to be moving in the molecular orbital, like in H2 plus. Okay, under the influence of two nuclei. Okay, this HA is it is atomic orbital. Okay, it is atom, so it is having atomic orbital. HB, again it is atom. Okay, so it represents atomic orbital. So when these two atoms combine, it forms molecular orbit. It forms a molecule. Okay, so here we are considering H2 plus. This is a molecular ion. Okay, now this electron will be present in the molecular orbital of H2 plus. Okay, and this electron is under the influence of both nuclei, which is HA and HB. But now here three cases may exist. Let's see which are these three cases. So three cases may exist here. The first case is, or first state is, in which the electron is present in the neighborhood of atomic nuclei A. Okay, suppose this is HA, and this is Hb. And let's suppose this Ha and Hb in the molecule, these are separated by distance r. Okay, and the electron is present. Like suppose in the first case, the electron is in the neighborhood of, it is in the neighborhood of Ha. Okay, so as the electron is in the neighborhood of Ha, so here we will see, we can say, or we can assume that the effect of nuclei B, that is Hb, on the electron is negligible. It is negligible. Okay, because the electron is in the neighborhood of A. So here the wave function for this state will be considered as psi A only. Okay, where psi A is the wave function for hydrogen atom. Okay, here we have two hydrogen atom in the molecular ion, which is denoted by Ha and Hb. Both atoms are same, both are hydrogen atom. So I am writing A and B just to differentiate the two nuclei. Okay, and the wave function, the wave function will be, I'm representing the wave function of atomic orbital by psi. So it is psi 1, okay, and the wave function for B, it is psi 2. Okay, either you can write A or B or psi A. This is a way to represent. So here also we will write psi. Okay, so wave function for in the first state will be equal to psi A because the electron is completely in the neighborhood of A. So the effect of the second nuclei on the electron is negligible. So wave function is represented by psi A. Okay, and the second case is when electron is in the neighborhood of second nuclei. When this electron is in the neighborhood of second nuclei, now the effect of A nuclei will be negligible. So here we will consider that the wave function, or simply write the wave function in the second case will be equal to psi B. Psi B. Okay. Okay. So now there may exist a third state also. What is the third state? In the third state, electron may be under the influence of both the nuclei. Like in case of first state, electron is in the neighborhood of, or electron is under the influence of only first nuclei. So wave function is psi A. In the second case, the electron is totally under the influence of second nuclei. So wave function is psi B. Now now in the third state, this state may also exist. In the state third, electron may be under the influence of Ha and Hb. Suppose electron is present over here. Okay, so it is under the influence of nuclei A and it is under the influence of nuclei B. Now the wave function for in such case will be equal, the wave function in such case will be having the contribution from psi A, okay, and from psi B. Okay, so the wave function for the state 3 will be having contribution from psi A and psi B. Now, how to represent the wave function for third state? So, wave function for third state will be equal to psi A plus psi B with some constants multiplied with these wave functions. Okay, so this CA and CB, these are known as mixing coefficients. CA and CB, these are known as mixing coefficient. Mixing coefficient. Okay, and these coefficients are adjusted in such a way that this wave function, it provides the upper bound to the true energy of this system. Okay, as we know, H2 plus, it is a hydrogen molecule. The energy of this system, it is solved by approximation method like variation method or perturbation theory. Okay, so here also we will apply the variation method to find the energy of the system. Okay, because it is a here we have multi-nucleus. Two nuclei are present here. So Ca and Cb, these are the mixing coefficients. Okay, and we will see how to find the energy of this system. So to find the energy of the system, we will use variation principle. Okay, so now we will try to find the we will try to find the energy of this system. Energy of this system, that is E, can be found by variation method. Variation method. We know the formula of variation method. It is equal to, for energy, okay, it is equal to integration psi h Hamiltonian, which is energy operator, into psi star d2, again divided by psi star d2. Okay, so here we are considering that our wave function, it is real. Okay, if it is real, then psi will be equal to psi star. And one thing more, are the operator, these are Hermitian operators. These are Hermitian operators. Okay, these are Hermitian operator. So if this is Hermitian operator, then it will follow the Hermitian equation. Okay, now let's find out the energy of hydrogen ion system. Okay, we know the wave function when electron is under the influence of both the nuclei. So in that case, the wave function is represented by Ca psi A plus Cb psi B. Okay, so here we will substitute the value of psi in the energy expression. Okay, from this we will get the two equations. Okay, so we know the variation principle. In variation principle, first we select the trial wave function that we have already selected. Second thing is, then we find out the variation in energy with respect to the coefficients, and then we put that equals to 0. Okay, so first we will find out the energy expression by substituting psi. So psi is Ca phi A plus Cb phi B Hamiltonian. Here I have written psi and psi star both are same. So I'm writing psi only. Means I will not put psi star here. Ca phi A Cb phi B into d2 divided by psi star, means Ca phi A plus Cb phi B Ca phi A plus Cb phi B d2. Now we will solve this equation. So we will solve these integrals. Okay, how we will solve? We will solve the brackets and we will separate the integral. Okay, so in first case, we will multiply this first term with the second bracket. Okay, so here we will get Ca whole square phi A, and here in between we have H, which is Hamiltonian operator. Then we will write psi A. Again, we will multiply the first term with the second term of second bracket. So Ca, Cb, these can be written together because these are only the constants. Okay, but we cannot write psi A and psi B together because in between we have operator. So we will write psi A H cap, sorry, phi B plus, then multiply this term here. You will get Cb Ca psi B H cap, sorry, phi, it's phi phi A plus then C square B. Here we have psi B H cap psi B H cap phi B. Okay, and bracket close. Here we have D two divided by multiply. Solve the lower term also. So here also we will get CA squared. Now here we don't have any Hamiltonian operator, so we can write psi A into psi A by psi square A. Then CA CB phi A phi B plus CB CA phi B phi A plus C square B phi B whole square. Okay, so this we will get. Now we will separate each integral here. We will separate the integral. Okay, so as C square, every C term is constant, so we can write it out outside of this integration sign. So I will write first integral as psi A H psi A d2, and second integral as CA CB outside integration sign. Rest of the term will be same. Again CB CA phi B H phi A d2 plus C square B phi B H cap phi B d2. So here we have separated integrals. Now similarly in the lower term also we will write C square A integration phi square A d2 plus CACB phi A phi B d2 plus, sorry, here we will write CBCA and phi B phi A d2 plus C square B integration phi square B d2. So here we have separated every integral in upper and lower term. Now we will introduce few notations here for these integrations. Okay, so here we are introducing few notations. So we will replace these integrals with some notations, and these notations are very, very important. So the first integral, which is equal to integration of psi A H phi A. It's phi A. This can be written as H. Okay, and here we have two functions of same nuclei, that is A and A. So it can be written as HAA. Similarly, the second integral can be written as HAB. Okay, and the third integral can be written as HBA. Okay, just keep the order in the same manner of these alphabets. Similarly, phi B H phi B can be written as HBB. Okay. Now similarly we will give the notations to the terms which are in the lower integral. The integrals in the lower term, that is your psi square A, it is represented by SAA. Okay, and psi square B, it is denoted by SBB. I will tell you the meanings of these notations. And psi A sorry, it's phi A, phi B, it is SAB. And phi B, phi A, it is SBA. So these are the notations that we will write in place of these integrals. Okay. Now let's write the simplest. Now let's use these notation in place of the integral. Let's see the expression of energy now. Okay. So I'm going to write the expression of energy by using these notations in equation. You can mark this equation. Okay. Any number you can mark this equation as the first number. Now we will use these notations. So we will get E equals to CA squared HAA plus CACB HAB plus CBCA HBA plus C square B HBB. Okay. And in the lower term, we will write CA squared SAA plus CACB SAB plus CBCA, this is CBCA SBA plus C square B SBB. Okay, so this is the simplest form we have written after using these notations for the integral. Now students, here we have two notations, HAB and HBA. Okay, so these HB and HBA, these are equal. We consider these notation equal because we are solving we are solving for H2 plus ion. Okay, H2 plus ion. So here the nuclei are same. Okay, so here the nuclei are same. So that if nuclei are same, that means the A nuclei is equal to B. Okay, because both are hydrogen atoms. So nuclei are same. So the integral of the integral of corresponding to this notation and integral corresponding to this notation will be equal. And you know one thing also that the Hamiltonian, it's a Hermitian operator. It's a Hermitian operator. Okay. And you know the condition for Hermitian. Suppose we have two operators, psi A, H psi 2. Okay, D2. Then it is equal to, we just replace the wave functions, right? So psi 2, H psi 1. Okay. So these two are equal. Okay. And these two represent, it represent H12 and it represent H21. Okay, so if your Hamiltonian operator is Hermitian, that means these two integrals, okay, or these two notations are same. Okay, so here we will write AB only. In place of BA, we will use AB because HAB and HBA both are equal. Similarly, here also SAB and SBA both are equal. Okay, so we will write here SAB and SBA also. You can write SAB equals to SBA. Okay, so these are also equal. Now we will further simplify the integrals and we will write E equals to CA squared HAA plus 2C1. Now we will add these two terms. Okay, 2C1 C2 HAB plus CB square HBB divided by the lower term, it is CA square SAA plus, again we will add the two terms. Sorry, यहाँ पे भी A आएगा, B. CACB SAB plus C square B SBB. Okay. So here we have found the expression of E. Now, what is the next step in the variation principle? The next step in the variation principle is to find the differentiation of energy or variation in energy with respect to these coefficients. Okay, so you can mark this equation too. Now we will find out curl E by curl CA, and we will find out curl E by curl CB, means we will find the differentiation or we will find the variation E with respect to CA and with respect to CB, and then we will put it equal to 0. After putting it equal to 0, we will get the value of energy. Okay, so we will get the two equations which can be written as in the form of determinant. So let's find out the curl E by curl CA. To find curl E by curl CA, first we will modify the second equation. What we will do, we will just cross multiply this. Okay, so I'm cross multiplying E into C square A SAA plus 2CACB SAB plus C square B SBB equals to this term C square A HAA plus 2CACB HAB plus C square B HBB. Okay, now we will differentiate. We will find the differentiation. So here you can see we have two functions. This is function A, this is function B, means first function and second function. So you know we find a differentiation of two functions, two different function by product rule. So here we will apply the product rule. Okay, so first we will keep this E first function as it is, and we will differentiate the second term with respect to A. So here you will get 2CA SAA plus 2CB SAB. Okay, here we have only C square B na. So if we differentiate it with respect to CA, then we will get 0. Here the differentiation of this with respect to A is 2CA HAA plus again differentiation of this term with respect to A, you will get 2CB HAB, and third term will be 0. Okay, so you can see we have 2 in each term, so it will be cancelled out. Okay, wait. Here I have missed one term. Okay, this is the first term, this is the second term. So first I have kept as it is, differentiation, I have differentiated the second. Now we will keep the second term as it is. This is the important part. Second term as it is. And we will differentiate first with respect to this. Okay. Now we have differentiated this equation with respect to CA. Now what we will do to find the value of to find the value of energy, we put it equal to 0. Okay, so we will put it equal to 0. So this term will be 0. That means the second term, this whole term will be equal to 0. Now we will be left with E. Also, as I said, all the terms contain 2, so I'm not writing 2 because it will be cancelled out. So I'm writing CASAA, just exclude 2. CBSAB equals to CAHAA plus CBHAB. Okay, now we will rearrange this equation. Okay, I will shift these terms. I will shift these terms to the right hand side. Okay, so how I will write the terms containing CA together. So here I have CAHAA. Okay, and from here I will get this term CAESAA. Okay, now I will write the second term CBHAB. Okay, and I will shift this term after multiplying with E to this side. Plus CBESAB. Okay, equals to 0. Now I will take out is the CA because CA is common. Okay, so I'll take it out from the bracket and inside we will be left with HAA plus ESAA. Okay, plus CB also common. So here I'll write HAB plus ESAB equals to 0. Okay, so now students, we have got one equation. This is the one equation that we have derived. This equation you can mark as third equation. Okay, so when you so similarly when you find curl E by curl C2, okay, when you differentiate curl E with respect to C2, then you will get, I'm directly writing the equation here because no need to do the whole procedure to get the equation. So here I'm writing the direct equation after differentiating after differentiating E with respect to with respect to C2. Okay, so what we will get here, we will get the second equation that is equal to, here I'm writing. So it will be equal to here we have AB. Okay. Now what will happen in the equation? These the coefficient of CA and CB will be interchanged. Okay. What will be the difference? The coefficient of CA and CB will be interchanged. Okay. So here I will write, this is AB. So here we will write BA. Okay. HBA plus, so this will be the difference. E into SBA. This will be the difference. And with CB, we will write H. Here we have AA. So here HBB will come. Okay. ESBB. This is only the difference. Okay. And so this is the next equation, fourth equation. Now these two equations can be written in the form of a determinant. Okay. So how we will write the determinant? These two equations, they form the determinant that is known as secular determinant, and which is equal to 0. Okay. So here we have two coefficients in the first equation. Okay. And two coefficients in the second equation. So the order of determinant will be 2:2. Means here we will be having 2 row and 2 column. Okay. And the first element of this determinant will be coefficient of CA. Okay. And the second element is and the third element, this is the first row, first column. This is the element of first row, second column. And this is the element of second row, first column, which is HBA plus ESBA. And the last term will be HBB plus ESBB. Okay, so so students, we have solved up to the determinant. This determinant is known as secular determinant. secular determinant. Okay. So in this first video, we will solve the linear combination of atomic orbital for H plus ion, H2 plus ion up to this determinant only. Okay. In the second part, in the second video, we will continue. We will continue and we will see how to get the energy, this value, how to get the energy by solving this determinant. Okay. And we will find the equation for wave functions also, and then we will normalize it. So we'll see you in the second video. Thank you so much.